Solid state. Solids are substances having definite shape and definite volume. In solids, the particles are closely packed and the force of attraction between the particles is strong. Now, the solids are classified based on the structural features as crystalline solids and amorphous solids. In crystalline solids, long range order of arrangement, whereas in amorphous, short range order of arrangement. Then sharp melting point and heat of fusion, no sharp melting point and heat of fusion, anisotropic in nature, isotropic in nature. Anisotropic means physical properties are different in different directions, whereas isotropic means physical properties are same in all directions. Crystalline example quartz and diamond, whereas in amorphous it's plastic and rubber. Now, based on nature of particles, it is divided into molecular solids, ionic solids, metallic solids, covalent solids. Crystal lattice. The regular three-dimensional arrangements of constituent particles of a crystal in space is called crystal lattice or space lattice. Unit cell. The unit cell is the smallest repeating unit of a crystal lattice. Types of unit cell. Primitive unit cells. Here the constituent particles are present only at the corners of the unit cell. Centered unit cells. Here the constituent particles are present at the corners and other positions of the unit cell. These are mainly of three types. Body-centered unit cells. Here constant particles are present at the body center and at the corner. Face-centered unit cell. Constant particles are present at the center of each faces and at the corners of the unit cell. End-centered unit cell. Here the constant particles are present at the center of any two opposite faces and at the corners of the unit cell. So in these three there are constant particles at the corners of the unit cell, plus depending upon body centered it's on the body, face centered it's on the faces, and end centered it's on the center of any two opposite faces. Number of atoms in different cubic unit cell. Primitive, or it's also known as simple cubic unit cell, it's 1. So we'll take it as 8 into 1 by 8, so equal to 1. Next, for body centered cubic, it's 2. So for that, particles at all corners and at the center. So this is 1 plus 1 equal to 2. Next, face-centered cubic, FCC, it's got 4 particles at the corners, center of each face. So this is 1 plus 3 equal to 4. Close packing in solids. In solids, the particles are closely packed. In close packed structures, particles are considered as hard spheres. Next we will see packing efficiency. The percentage of the total space occupied by spheres is called packing efficiency. Packing efficiency equal to volume occupied by all the spheres in the unit cell into 100 by total volume of the unit cell. A sphere means it's the same as the particles. FCC, the packing efficiency is 74. In BCC, it is 68. In simple cubic, it is 52. Next, we will see imperfections in solids. that is crystal defects. The deviation from the regular orderly arrangement of particles of a solid is termed as crystal defects. The crystal defects are broadly classified into two. Point defects. The imperfection is around a point in a crystalline substance. Line defects. The imperfection along a row. The point defects are of three types. Stoichiometric defect, which is also known as thermodynamic point defect. The defect which do not disturb the stoichiometry of solid. The stoichiometric point defect is again divided into two types: Schottky defect and Frankel defect. Schottky. Due to the missing of equal number of anions and cations from the lattice site. Frankel. Dislocation of cations from the lattice site to the interstitial site. Density decreases, density remains the same. Cations and anions have similar size, ionic size difference is large. Higher coordination number, lower coordination number. And a few examples for both the defects are given. Next is non-stoichiometric point defect. The defect which disturbs the stoichiometry of the solid is called non-stoichiometric point defect. Metal excess defect due to anion vacancies. In this defect, the anion is missing from the lattice site. To maintain electrical neutrality, electron is occupied in the anionic vacancies. This center is called F center or color center. Due to the formation of F center, the crystals become colored. For example, heating of NaCl in an atmosphere of Na develops yellow color, i.e., excess of Na in NaCl gives yellow color. Similarly, excess of K in KCl gives violet color, excess of Li in LiCl gives pink color. Next is metal excess defect due to extra cation at interstitial site. In this defect, extra cations are present at the interstitial site. To maintain electrical, also present at the neighboring interstitial site. Examples: when ZnO is heated, it loses oxygen and turns yellow in color. Here, excess Zn formed present at the interstitial site and equivalent number of electrons are also accommodated in the neighboring interstitial site. Metal deficiency defect due to cation vacancy. In this defect, some cations are missing from lattice site. To maintain electrical neutrality, an adjacent metal atom acquires extra positive charge. Impurity defects. It is a defect arising due to the presence of foreign particles in a crystal. Example: when molten NaCl is crystallized in presence of small amount of SrCl2, some Na plus ions are replaced by Sr2 plus ions and some cationic vacancies are formed. The number of cationic vacancies produced is equal to the number of Sr2 plus ions occupied. Another example is a solid solution of CdCl2 and AgCl. Next we will see the properties of solids. Electrical properties. Conduction of electricity in metals, semiconductors and insulators. Band theory. According to band model, in metal there are two types of bands: valence band and conduction band. Valence band is a lower energy electron occupied band and conduction band is a higher energy occupied band. In metals, the valence band is either partially filled or it is overlapped with conduction band. So, electricity can easily flow from the valence band to the conduction band. In semiconductors, there is a small energy gap between the valence band and the conduction band, and only a few electrons can enter into the conduction band, so they conduct only partially. In insulators, the gap between the valence band and the conduction band is large, so they do not conduct electricity. Magnetic properties of solids. Paramagnetic substance. Substance which is weakly attracted by magnetic field. Paramagnetism is due to the presence of unpaired electrons. They do not show magnetism in the absence of magnetic field. Example: oxygen, Cu2+, Fe3+, chromium 3+. Next we will see diamagnetic substance. Substance which is weakly repelled by magnetic field. Diamagnetism is due to the presence of paired electrons. Example: NaClH2O, benzene, etc. Ferromagnetic substance. The substance which is strongly attracted by magnetic field. It retains magnetism even in the absence of magnetic field. Ferromagnetism is due to the spontaneous alignment of magnetic moments in the same direction. For example, iron, cobalt, nickel, etc. Antiferromagnetic substance. The substance which are expected to have high magnetic moments, but actually it possesses zero magnetic moments. It is due to the alignments of magnetic moments in the opposite direction alternatively. Example: manganese oxide. Ferrimagnetic substance. The substance which are expected to have high magnetism, but actually it possesses small magnetic moments. Here magnetic moments are cancelled each other. Ferromagnetic substance, antiferromagnetic substance, and ferrimagnetic substance. So I hope all of you understood today's chapter, and if you have any queries you can comment below. I'll be happy to answer your queries. Wish you all the best.